Okay, so the session is being recorded. So hopefully we have, good, I'm glad the audio is good. So welcome back to our first virtual session. I'm kind of learning as I go. I've been trying to prepare this all week, but it's been hard to do without students. I wanted to have a virtual test, but I think as you may have guessed, I became symptomatic on Sunday, so I've been doing the best I can to recover, and I feel a lot better now, but I definitely can't leave my house for a couple weeks. So, so we'll make do with the best we've got. So as you can see, I'll just go back to my finger here. Let me know if I think you can see something and you can't see it. I think that's going to happen often. So I have my clicker here, and again at the bottom, I hope, oh, the clicker only stays there. So at the bottom of your screen, where it says you're in and you have your, I think you saw the instructions, I just want to make you all aware again of that raise your hand. If you have a question or something, it'll pop up and let me know you have a question, and you can turn your microphone on and ask, because it would be good for the whole, if your typing it isn't good. The reason I don't have you all doing the video and the audio is because a lot of you have already told me you don't have bandwidth. I've gotten emails about that, concerns about that, so it just keeps everything moving, you know, more swiftly with the internet and not overloading the data. If I start mumbling to myself, please let me know. That might happen since I don't have all of you here. It's just, it can't be avoided. So anyway, let's pick up where we left off with a tiny bit of review, okay? So we last left before we before we ended our break. We ended or our break, or pause is a better word, is we started talking about kinematic equations in constant motion. And we had this list of equations, which I hope all of you can see here in this slide. At least Blackboard tells me that should be up. So, so when we look here, we'll notice we were able to get these equations from integrating. I'm going to go to the blackboard or the whiteboard. Actually, no, wait a minute. I don't need to do that. Hold on. Okay, I'll go back to the chat. Let's go here. Okay, so you might remember that we could get, all we had to do was assume that A was constant. This is weird, right? I need to move the drawing pad to a more comfortable place. I wanted right here. There we go. All right. And then all we had to do is integrate A with respect to time, and that gave us that equation right there, okay? As you can see, the pencil is not perfect. Let's clear that stuff. So we can start from that assumption of constant acceleration, and we can get equation 1 here. Oh, wait a minute. See, this is what I mean. Equation 1. And if we integrate again, if we integrate this equation, you'll notice that the integral of v, right, will give us our x naught minus, or x minus x naught. If we integrate the v naught term with respect to t, we get that t. And of course, if we integrate 1/2 or at here, we get 1/2 at squared. Now, with these two equations, you can eliminate any variable you want and get these other three equations, okay? And this equation is, we get from algebra, is usually the most, after these two, the most used equation. But whenever you're looking at a kinematics in one dimension, what you really have to do is figure out what's missing, right? What do you have, what do you not have? So if you're solving a problem, if you have some problem, we're going to solve a problem in a minute, you can make a table of variables and just say, like, ask yourself, hold on, I'm gonna get used to this. Will, I hope, get better as the semester goes on. So what do you have? What do you have versus what am I missing? Okay, so that's what you have to ask yourself. Now, of course, this is the nice thing about this is I can hear that craziness. Okay, so what I want to do is I want to move on now. We're going to be more specific. And as I told you before, we'll often see this where we started generally. So you'll remember, or if you recall, we started with general definitions of, oh crap, there we go. We start off with general definitions of velocity. Remember, velocity is equal to dx dt. And acceleration is equal to dv dt. Remember, we started off, this is always general. This is always true, okay? But we've put this constraint here for these equations to get constant acceleration, or we've put in the constraint of constant acceleration to come up with these equations. So these are limited. We've made an important assumption. And now when we go to free fall, which if we go to the next slide, we talked about this before. We saw that video of the feather and the hammer dropping on the moon. So here we have sort of an apple and a feather, same thing. So keep this in mind. Keep that video in mind. You can watch it again. It's a famous video on YouTube to show that everything falls at the same rate. And so what we're doing is we're looking at the special case here, where I'm going to see if this is actually easier than advertised. Actually, this might be easier for me to do it on the mouse. I don't know. I'm going to give it a shot. I got this tablet thing, and so far it's a real pain in the butt. But here we're going to say that A is equal to
Professor?
G.
All
right. I might do a quick poll on who likes the mouse writing better and who likes the tablet writing better. The tablet was only about $25, so I guess it wasn't the worst thing in the world, but this might be more comfortable. So we're going to have A equals to G, and remember that G is equal to 9.81. Oh, it's not going to give me the point. Oh. Hold on. Someone had a question. Elvin had a question. What was your question? You can put on your mic if you want.
Oh, I pressed the button by accident. Could you hear me?
Oh, where'd you go?
Hello?
Hold on. Oh, I think I have to go to participants list too. Hold on.
Sorry, I went to the wrong thing.
Hey, what was the question, Elvin?
Oh no, I pressed the button by accident.
I can't hear you. Hold on, let me turn up my volume. Maybe my volume's...
I pressed the button by accident.
Okay, try going now.
I pressed the button by accident.
Professor?
Hold on. All right, I can't hear you, which is not great.
By accident.
I've got my volume way up, and I can't hear you. Hold on, let me see if there's some sort of sound setting that's... No, everything's high. Oh, wait a minute. Everyone please silence the mics. There's an awful echo. Oh, that's probably... I can't hear anyone's audio.
Hello.
Hello, hello. Can you hear me?
Hey, yeah, I don't think you can hear us.
That's
Hello,
weird.
not. That's strange.
Yeah,
right?
I don't know, man.
Yeah, everyone should silence their mics if that's a thing. I should be the only one talking. Oh, you can hear each other.
Yeah, we can hear
I can't
each
hear you
other.
guys.
Yes, we can hear
That's
each
irritating.
other.
See, I see that Fatima's mic went on. I can see the mic there, but I can't see it talk. Oh, brother, I'm going to have to figure this one out. Hold on, let me see if I can select a student to here. Attendee controls. And I've been largely maintaining the muted mic. Okay. I've got a question from Zilla. Yeah,
hello.
that's weird. I should be able to hear you guys too. Okay, so Zilla's got a hand up. What's the question? I can't hear you talk though. That's infuriating. Why can't I hear you guys talk? Okay, I can mute all. Unmute.
Hello,
All
can you hear
right.
us now?
I think you're gonna have to ask questions through the text for right now. And yeah, if everyone could just mute their microphones so that you can at least hear me. I don't know why I'm not hearing everybody. I'm gonna have to figure that one out. That is very strange. I can even see my hand, and my mic says I'm talking, and my speakers are on. I don't know why Blackboard is not letting me hear you. That is really, really strange. Transmit the sound. The user might not be using headphones. It might be me. You might be getting sounds from me because I'm certainly not using headphones. I don't have Bluetooth on this computer. The builder was very, overlooked it. So you might be getting echoes from me. I don't know. There's birds and stuff. I could try turning my volume down. That shouldn't really do it though. Hold on. Maybe it's the Dalek's fault. It might be. I don't know. Is everything okay now? Because I'm the only microphone on. So any echo, is the echo still a problem? Okay. Well, I think I'm going to keep going for now and hope that we do a better job with it. I'm not sure where the echo is coming from. I mean, I have birds. There's nothing I can really do about that. So it shouldn't be too bad. But let me go back and through. I'm really sorry about that audio. This is one of those things. I'll probably spend most of tonight looking up why I can't hear anybody. So I'll just keep going with the lecture if that's all right with everybody. If you have a question, do the raise your hand. But then we have this chat thing. If you look where it shows everybody with the bubbles, you can put there. Oh, someone's already helping me. Go to setting. All right. My speaker volume is 100%. Set up your camera and mic. Those have already been set up. Speaker volume is, yeah. I'll just report an issue. I'll just say I can't hear others. And then I'll submit it and see, maybe they'll give me a thing. Well, it's technology. Everything has a problem. I don't really know how to use Zoom. I don't have the whole thing. So efficiency is it's not more efficient at this point because I just don't know how to use it. So and I'm not going to stop mid-lecture to figure out new technology. I'm not that young. So this will work for now, and plus you can get the lecture, and I already have the recording going on, and the recording already goes on Blackboard. So we'll try and get this issue fixed as we go on. Otherwise, we'll keep going. Okay, so A is equal to A is equal to G. G is equal to 9.81 meters per second squared. Okay, and that's not going to look great. I think we have it written better down here in the next slide. 9.8 meters per second squared. Let me put that there. So anyhow, so we're going to be replacing that acceleration value with this value of g, and we're going to do that to solve problems. And this is what we call free fall. All right. So if we look, I asked you before the break to try and replace in these set of equations a with g. And I think you'll remember I said something about the negative sign. You'll notice when I wrote g, and we have it here, we don't set it equal to negative 9.8 meters per second squared. Okay, we set it equal to, or we don't. It's just 9.8, and you put the minus sign in the equation as you look at it and use your whatchamacallit, as you solve a free fall equation. So I wanted to solve a problem. We got to this problem, and you'll notice, and I wanted to solve it to show you how to sort of deconstruct a free fall problem. Okay, so let's show view controls. Okay, oh, all right. So if you look at this problem, this is a simple problem, and I'll go to. Can you all see me on the video? I don't know if you can see me because I think I can only show one thing at one time. Okay. So, so if I throw something up, I'll move back a little. What do I have? I have all sorts of interesting things here. If I have a flashlight and I throw it up like this is the problem, right? We have something being thrown up and coming down. And you can see the trajectory is given here. In red, we go up, the ball reaches a maximum height and comes down. So you'll notice that with everything we throw. When you throw things up, they don't just keep going on forever. In fact, they stop and come down. And looking at and identifying those features is an important part of learning of free fall motion problems. So let's look. You'll notice that we have a pitcher tosses a ball up along a y-axis with an initial speed of 12 meters per second. But you'll also notice that some other stuff is given here, right? So does anyone want to take a guess from typing? I'd say put on the microphones, but what's given here that's not being given? So I have an initial speed, right? I have a v naught. I have a v naught. Time. Good guess, but we don't really know anything about the time, right? Because if we look at time, it takes time to go up and it takes time to go down. So we're not really, so right now we're not really, nothing is really given about time. But we know, for instance, we can have an initial position, right? X naught, we can always set our initial position equal to 0. So we can always just say, okay, I'm going to say this is y0 and this is where I start. That's my initial position. Oh, shit. See, this is what I mean about the pointer. We can always say that this is the initial position, and therefore, that's where the motion starts. Okay? And we go up, and we go down. Now, what is given here without being given is actually the acceleration. Because the acceleration, right, is equal to g. All right? And if you want to be really crafty with it, you could say it's more correct. I don't know how people get this thing to work so well. Everyone's talking about this tablet like it's the God's gift to the world. You could say here that this is equal to, a better way to say this is A equals negative G, right? Equals minus 9.81 meters per second squared. All right, now, when we look at this, notice where the minus sign came in. I put it in after defining A. So if we go back to that list of equations, right, if we go back here and replace A with minus G, you'll start to get a nice set of kinematic equations that apply to free fall. So let's go further in the example and see with that given information what they want us to find. All right, so the first question is, how long does it take the ball to reach its maximum height? So you'll notice we can't be given time, right? Because the first thing they want to know is, well, how long does it take to reach the ball's maximum height? So I can look at this, and the first thing you really want to do is go back to that table of equations. But usually what I like to do to get some experience with it is guess and check instead of looking at it. It's probably shorter to just look at it, but you get a little more practice if you just guess. So I know, for instance, that I have the one equation. Okay, I want my pen to be here, so I want my screen to be here. That V naught equals V naught plus AT, right? This is a simple question, a simple one. And I might be able to guess from the solution or figure out if this is true. Now, I have V naught, right? That's given in the problem. It's right here. I have A, right? With this equation for free fall, this becomes V equals V naught minus GT, right? So, someone's already got it, but let's be sure we know how to get it, because answers are good, but only if we know how to get there. So, Daniel, since you got the answer, let me ask you, did this equation work? Good. Now, I know I have V naught and G. What was the answer for V? Right. Good. So I don't know. I know text is annoying to follow, but Dan is correct here. And what he said is that V is 0. And remember what I said, and this is again goes back to that part about physically interpreting the problem. We know at the top, oh lordy, you can already tell I'm gonna hate shifting between the mouse and the cursor. We can tell at the top, right? We switch directions, and whenever we switch directions, that's indicative of the ball coming, or any object really, coming to a stop. So in order to change directions, you have to cease going the direction you're going, right? So if we do that, then we can see here that this V, I'll get fast forward as things go on. This V goes to 0. Okay, Tala, I'm ready to see your question, but I can't hear yet, so I have to figure that out. I know Zoom has the hearing, but I don't, I don't have that set up. So, okay, great question. So the question is A always equal to negative G? So in a free fall problem, A is equal to negative G, right? And the negative indicates, if you can see me, that the gravity is always pointing towards the Earth. Yeah? So we're always pointing towards the Earth, going down, because we don't float away, right? So, so in that sense, when we're looking at a free fall problem, A is always G. Excellent question. Even when the ball is going up, because remember, if something is moving up, right? If I throw something up, gravity is still pulling it towards the ground. So as we go up, gravity is making it slow down because it's actually pointing down, and then it stops, and then it starts accelerating towards gravity. So the gravity A is equal to negative G throughout the entire free fall process. So basically, when I leave here, and this is a good follow-along problem, as soon as the ball leaves the pitcher's hand, right, negative g, the gravity is acting downwards, right? And that's causing the ball to slow, oh, you can't see that. It's causing the ball to slow down. Now, when it gets to the top, gravity is still acting on the ball, and nothing's changed. It's just now the ball has stopped, and it's turning around and accelerating now, getting faster and faster towards gravity, or towards the Earth. So you'll notice that the gravity is the same whichever point in the process you pick, or the acceleration is the same, rather. The acceleration is always equal to gravity. Right, in a free fall problem, right, we always want to be sure we're only talking about free fall. So, because that's the important point. We don't want to just start willy-nilly going, oh, A is just always equal to minus G. A is equal to minus G in a free fall problem. But in a free fall problem, that's all it's equal to. Another good point this question brings up is that when we have an acceleration and we expand our discussion to forces, it's going to be basically it can be confusing what's causing or not causing a force. And my rule for this is ask yourself what's causing the force, right? When you release something, you know that the Earth is causing it to come back down towards it. If you can't identify what's causing something to be pushed or pulled, you're probably making something up in your head. This seems counterintuitive now, but when we talk about forces, you'll see exactly what I mean. Jesus. Okay. It was the cough, not the question. Okay. Yes. Good. Okay. So I think we have this problem, but I want to show the full simplification of it, which is if we have this, then we can go 0 equals V naught minus GT, and that's going to imply, right, that T will be equal to V naught over G. And you'll notice we get the positive because we have that velocity equal to 0, and that makes everything sort of nice and positive and happy, right? So this is our expression for part A, all right? So let's go and do so look at that for a minute. I'll give you a second or two to write that down. Remember, we're being recorded, or recording all this, so ideally, even all the part about me not wanting to do Zoom at the moment, the situation with Zoom has changed as well. So all the messages are recorded too, so we should be able to look at the questions and things like that. So any questions, any more questions on this? I think I got them. Just be sure to raise your hand. And let's move to part B. All right, this is going to go away. Can't help it. All right, so the next thing is, what is the ball's maximum height above its release point? All right, so you'll remember that. So now the question is asking, what is T? What is T here? Right, at that point. So, no, that's not true. I messed that up, right? It's what is, that was part A. Now for T, we have what is, for part B, we want to know what is delta Y. At this point, and in order to figure that out, we need T from part A. Right? So now we can look at I'd say plug it into your calculator and give it a shot. 1.22 seconds sounds right. And V naught equals there. But I'd have you check that for yourself. Yeah, so I think we'll go by consensus there. So we have T, and now we're going to move on. We want delta Y, right? Now again, we can put Y naught equal to 0 at the bottom where the pitcher's hand starts, and we want V naught T minus 1/2 GT squared. I want you to notice again what I did with the minus sign here. I added the minus sign once I evaluated the original equation. It's a subtle point, but it's really important. You don't want to keep putting your minus sign embedded in the G. You always want to be very explicit with it, because if you're not, you'll end up with off by minus signs, and everything is built to sort of work out. So if you start getting imaginary numbers or negatives when you really know you shouldn't get them, not just because you don't like them, that's pretty indicative that you've arrived at a place where you don't have the the sign. So if we look at this, we have T from part A. So we know V naught, right? Again, that's here. We know G, right? We know that T is equal to 1.22. Well, we'll say, what is it? What was it? V naught over G equals 1. What did you say? 1.22. 22 is fine. You can plug this in seconds. You want to be careful too. So you plug those seconds into here, and now you have one equation and one unknown. You use half of T. No, it's the halfway point in the journey. Ah, very good. No, that's a good point, but you could see where it could get confused. We solved explicitly in part A for the time it takes to get to the top. So the time at the top corresponds to this particular delta Y. So we're actually in good shape. But you're going to be right on for physics 2 when you shoot the sound beam down the tube, because that you have to multiply by 2. Yep, nope, we did not. So you should be able to plug in numbers. Does anyone want to report a number for this, for delta Y max? You can even write it like that too. Delta Y max. So it seems that, oh, I should have written the max here. Equals, okay, so 7.3 sounds good. Don't forget your units. Those will be important. Yeah, we're all getting the same thing. Calculators vary, Some of you probably put in 9.8. Some of you put 9.81. Maybe one of you put in 10. So that works. Okay. But are you getting an idea of how to... the important thing here is to see sort of how the equations are applied. So hopefully you're getting an idea of how to do that. Let's go through, continue working through the example. Oh, right, the pad's there. Oh, there's all sorts of doo-doots and sounds. Okay. All right. And then see how long does it take the ball to reach a point 0.5 meters above its release point. Now, you'll notice here, we solved for t to the top. Let me stop being stubborn here. T to the top. And we got delta Y max here, right? But now we want an intermediate value. Yes, the unit is meter. Good, very good. We want this to be our Y max. So now we have an intermediate value. We want some new delta Y and int, and here we have a T intermediate. I'm going to put a semicolon here. And you'll notice they give us the new delta Y, right? 5 meters. So now all we have to do is say, okay, let's go back and look at our two, let's go back and look at our table And here this might be helpful, right? So we know the acceleration in all these, so we're not going to use the one that's missing A. So when we look at this, we have a position, right? And it wants a time. And we have the initial velocity still. So we could use 215, and I think that's going to be the best option. Solving the quadratic can seem a little bit much, but let's take a look at our other option. It might be tempting to want to use this equation here, but you'll notice that you don't have v, you're introducing a new unknown, whereas with 215 here, we have our new delta y, right? We're recasting it. Remember, you can name anything you want. It's not fundamentally x or y. I want to break you from that habit from calculus. We have v naught, we want t, and we have a. So v naught is v naught is not 0. Look at the problem. V naught is when for v naught to be 0, you'd have to drop it from the top like this. That's v naught equals 0. Here, there's some initial velocity which leads it to rise, stop, and then fall. And you'll notice in the problem, if we go back, let's go back. The initial speed is given here as 12 meters per second. So that will pertain through the whole problem. All right? So, looking at that, we can go and write our equation. Let me get to the pencil. Delta y, which we have, equals v naught t minus 1/2 gt squared, right? And if you know delta y, and if you know delta y, and you know v naught, and we only have t as the unknown, it's not the most comfortable thing, but we can use our quadratic formula and say that t is going to be equal to, because this is just a quadratic, so I believe it's, right, b squared minus this, oh no, it's b plus minus, hold on, I gotta erase everything. So for the quadratic formula, we have t, I think is it negative b or b? I'll let one of you look that up on the internet. Plus minus the square root of b squared minus 4ac. It's amazing how much math you forget when you get old. Over 2a, right? So now what we have to do is let's go back and rewrite the equation that we cleared up here and identify what the hell is b, what's a, and what's c. So we have here delta y equals BB, the list of courses that I don't know what that means. Delta y equals, getting email during a lecture is a terrible consequence of this, which is t squared. Okay, so let's put this in a quadratic form, all right? So we can write this as 1/2 g t squared, right? Minus v naught t plus delta y equals 0. Yeah, you can use a completing square. Anything, this isn't a math class. There's, I usually just power through things with math. And yeah, any way you want to do it, just do it. I just want to point out, in case, I will show a way, not always. But yeah, completing the square, totally. if you've got it. But generally, completing the square, I think, is easiest with nice round numbers. Here, you can notice that this is A. You've got V naught minus V naught here is B. And then you have, this is C. So this is your A, right? Your B, your C. I'm not going to go through the quadratic formula part. You guys can do that. Online quadratic is a fine way to solve the problem. I'm not going to tear you down for it. But for those of you who like to do math by hand, you know, this is how you'd set it up and do it. And particularly if you're doing this on a test where math quadratic may not be, well, I guess this semester it might be, although I really wish you wouldn't use the internet during the exam. I can say that. Now, I like John's answer here. He got 2 times, and I want to talk about that. If you go to the chat, it's currently the number that's up. He has, and I'll write it here, t equals 0.53, and t equals 1.91. No, 1.22 is the time to get to the top. So so remember, for part C, we're dealing with a different part. But we have two equations, or two quadratic equation gives us 2 solutions, and they're both positive. So we have 1.913. So now what you have to ask is, we know that the max height was 7.3. So we have to ask, right, are we on the way up or the way down? And this is interpretive, right? So because we know that the maximum height is 7.3 here, and we're looking for the height at 5 meters, we want to actually choose the lower time, the 0.0, all of these are in seconds, by the way, 0.52 seconds, or 53 seconds, I miswrote that, and because the 1.92 second, we come all the way back down here, and that's for when you're at the same height, but coming back down. Yeah. All right. So, right. Good, Nicholas. That's correct. Hold on. I need this to stop coming up. Right. Again, we get up here. This is where 1.22 seconds happens, and then everything after is falling. All right. So that took a little longer than I wanted with that, but I guess that's the best we can do, trying to figure out this and the current sound issue. So I understand the mathematical part, but why is V 0? V isn't 0. We just don't know what it is. Where did we put V equals 0? That's V 0. This is V initial. This is not V equals 0. At 1.22 seconds, it has to stop. Remember? So if we throwing something up, if it leaves my arm, if you can see my video, it stops and then turns around and comes back down. All right. So let's get started with vectors, and we'll take a quick I'll take a quick break in about 2. Yes, only for a moment, but you don't need to continuously stop. So let's go on to, let me go to this sharing content, share. All right. Nope, hold on. Share files. Hold on. Share now. Okay. So let's move on. Hold on. Will you allow? Yes, I'll allow it to see. Wait, why? Okay, it needs to just remember this. Okay. All right. Hold on. This has become annoying. gonna stop sharing that file. I can only do one at a time. This is obnoxious. All right, so, okay. No, this is, hold on. Now I'm starting to get really irritated with this. Chapter 3, share now. Okay, all right. So, getting sort of muddling through this as well as possible. Now, instead of doing an example, we'll introduce some new concepts, which are the vectors. Vectors are probably the most important concept we have in the entire course. They're very foundational. So as we go forward, let's take a look at some of our definitions and talk about them. So we'll go through these learning objectives and look at some of our hold on. Did this just bring me back to vectors or to the last chapter? This is like the Twilight Zone. Hold on. Okay, stop sharing that. Chapter 3, share now. Hold on. Okay. I might have to stop recording because if this doesn't just start working, I'm going to have to really start cursing. And I don't want to do that. So don't go back to chapter 2 now. Okay. All right. So hopefully you can all hopefully we're all still in it. Okay. All right. You're all in the room and we'll see what we have going. Okay. So, all right. Almost had to stop recording because I was going to yell at the blackboard and the screen. Believe me, there is no perfect thing. I would be yelling at Zoom too. I guarantee it. So vectors, you'll notice we start having a magnitude like we've had before. So a length of a line here, and direction. We have this arrow. This arrow sort of points to where we're going. All right, and just need to point that out. You have the length and the direction. So I feel like I skipped something here. Oh, good. I love when yeah. Well, you know, these will get better, I promise. They'll get better, I promise. If you look back to what we talked about in chapter 2, right, and we talked about one-dimensional motion, that even though it's one-dimensional, we still had to identify things as vectors because they could go either forward or backwards. We needed to distinguish between those two motions. So now the vector will let us generalize directions to our three-dimensional, spatial description of the universe. But when we talk about quantities that vector quantities, they have both a magnitude, a size, and a direction. All right, and vectors are mathematical quantities. Okay, there's a whole. You can take vector calculus and linear algebra and learn all about what it means to be a vector. Even though we don't go over all that mathematics, the things we define as vectors do follow those properties. And basically all we have to know is that a vector is a quantity with size and direction. This is one of those vector sounding things. I like to read this one, but it says here a vector quantity is a quantity that can be represented by a vector, and this harkens back to that math. So a vector quantity is just something that can be represented by a vector, and a vector is something that behaves according to the mathematical definitions of a vector, which we don't go over, so that can seem a little frustrating. Let me go back at here because I didn't see any questions. So you can see here that we have some examples such as position, velocity, and acceleration. Those should be the obvious ones, right? Vectors have their own rules for manipulation, and we're going to see that, for instance, things we took for granted, right? like commutativity in multiplication, does not hold for vectors necessarily. So you're going to find with vector multiplication, there's two of them. We'll cover them briefly in this chapter, the dot product and the cross product. Before we cover them formally, you're going to see that this equality does not hold, does not equal B cross A. So that's a little different, right? Where these are vectors. I need to put the lines on top. I'm doing the best I can here. Okay, so that does not hold. And this is actually really weird. This one you'll find easy and more comforting to actually do. But here you're taking these multi-dimensional vector objects, and when you do this product here, this dot product, you actually get a scalar. That is not a vector. So you input vectors, you get out real numbers. Here, in a more traditional type of multiplication, you get a vector, you'll get a vector from this multiplication, this cross product, but the commutation rule does no longer holds. So you want to keep that in mind, that these are different animals that you've been used to dealing with. Of course, a scalar quantity like time, temperature, energy, mass, speed is a big one. It's not mentioned here. I'm going to write it down here. Speed. Oh, well, they took away my one. Speed. Remember, speed is not velocity. All right? Speed is the magnitude of velocity. So those are examples of scalars. That's what we're focusing on here, the scalars. All right? So now that we can do that, we can look at some representations of vectors. All right? So you'll notice that the vector, it doesn't matter how we get, oh, rhyminy. It doesn't matter how we get from A to B, right? You'll notice you can go in the straight line if you follow this path, or you go do this roundabout path. It doesn't matter how you get there. All that matters is your initial and starting point, which just seems sort of familiar. Once you have those 2 points, you define the vector in the vector space. Again, vector space is just a fancy word. So here, if we look at these 3 vectors in A, we can see that all of the vectors are the same length, okay, from A prime to B prime. They look like they're in different areas, but they have the same length, and they have the same direction. So even though they're in seemingly different spatial areas, these 3 vectors are identical. All right, and as long as they're the same quantity, it's fine. So let's see here. Anything else to say about that? Oh, yes. Type away. I will lower the hand. We had a question. Yeah, Tala. So, yes, absolutely. Very, very good observation. Yes, both things must be equal. You'll notice I want to, this is actually good for the drawing. Let's look at a case where we have different directions. Oh, actually, I can use the, hold on, I can use the shapes here and make lines. So imagine we had another vector going the opposite direction, or the same length, right? But a different direction. I can do that here. And go back to pencil and put an arrow. Oh, crap. That's defeating the purpose. So you'll notice this is pretty much the same length, but it's a different direction, so they're different vectors, right? Yeah, if vectors are going to be equal, they need to be both the same length and the same direction. And you can notice if I have 2 pens here, hopefully you can see the stylus, you can see my red pen. I like to use pens because the arrows are natural. And for instance, you could pretend that they're facing opposite directions. These would actually be canceling, and because they're in opposite directions, they could lead to a cancellation of the quantities. This is easiest to see if you push or pull on something, right? If you have one of your little siblings available, you can have them pull on your arm, and you'll be pulling with one vector, force vector, they'd pull with another, and you'd get 0. But yes, in order for vectors to be the same, because a vector is a magnitude and a displacement, or a magnitude and a direction, both the magnitude and direction must be the same for the vectors to be equal. Very good point. Yeah. Okay, let's go on to some math relations. So the vector sum. Now usually I'd want to play on the board with this. Yes, they would cancel out. And for scalars, you only need magnitude. Well, for scalars, the direction doesn't exist. Think of things like time, or temperature is easier because sometimes we look at time as flowing forward or backwards. So there's like this, even though it doesn't have a direction, you can't just change the direction of time willy-nilly, right? I can't just say, hey, I'm going to go backwards in time and fix the the audio issue. But that being said, temperature doesn't have a direction. It can have gradients and it gets complicated, but if your room is room temperature, you're not going to, you're not going to have a direction to that. So scalars are just sort of defined. They almost don't make sense with a direction, right? Speed is just how fast you're going. Velocity has to tell you whether you're going north or south. So yeah. For the scalars, you only need magnitude, and in the opposite direction, they would cancel out because both the magnitude and the direction, or the magnitudes are the same, but the directions are opposite, and that gives you a minus sign. So, and it's because we have these two properties that you can change the minus sign in one or the other, which is what makes the math interesting, right? What I mean by that is when you're going to note when we write vectors. Hold on. When we write out a vector equation, and I'll write a simple vector. None of this will make sense right now. Plus bj, but this is where the direction part is. Hold on. These things with the hats are where the direction is, and these are the magnitude parts. And this is saying in the x and the y. We'll get to that in a minute. But the point here is that stuff can change in the direction or in the magnitude. And this is what creates vectors as interesting mathematical objects, because stuff can happen in either the direction or the magnitude, completely change the vector. So, but vectors, before we confuse you too much, because we probably already have, before we do too much, I'm gonna put here, or we're gonna look at basic rules. So you'll notice that vectors add. Basically what this is interesting, this is really fascinating from an abstract math point of view, because basically what you're saying is that the sum of any two vectors is another vector. That might seem trivial, but if you take some advanced mathematics, you'll find that this is not you can't take this for granted. That just because you have two of one type of object and you do something to them, you get the same object back. And as I showed you with the dot product, as we'll see in a little bit of detail later, probably tomorrow, that's not always the case. But let's look at how we do this. You'll notice again the actual path doesn't matter. We have a vector from A to B. Jesus, sorry everybody. I'm still getting used to this. We need a vector from A to B, and we need a vector from B to C. Okay? And then the resultant vector, you'll notice here, let me get the pencil. You'll notice that our resultant vector starts at A, and we can draw it to C. Okay? So you'll notice you start at the head, you start at the initial point, and go to the final. All right? But you'll notice that you put the two vectors together, and you'll notice when you add the two vectors together, you sort of do it like Legos. Like you have the end and the bumps, and you just connect the vector in. So if you take A and B, which don't necessarily have to form this nice triangle, they can be anywhere spatially, right? You could have it like this. You could have, that could be A, and then someone could give you B just like this. But now you you could get this A, put it here, get B, put it here, make sure the head goes into the tail like a Lego, and now you have your triangle, and that will guide you from A the starting point all the way to the end of C, and that will give you your AC vector. Okay. Now, vectors addition is commutative, which is nice. Well, that means that A plus B is equal to B plus A, and this allows the construction, because this is A plus B, this is B plus A, and I want to highlight that connective part here, right here, okay? This is where we're getting vector and plugging it into the A vector. Similarly, here we have the A vector. We're plugging it into the B vector. And I want you to notice that we have this quadrilateral method of adding a vector. So one way to do it is if you have A and B, you can make a quadrilateral. You'll notice this is, or a parallelogram rather, parallelogram method. So you can have parallel to B, parallel to A. You go from vertex to vertex, and that will give you the finished vector. So before we continue on with vectors, we'll take a brief break. So I think what I'll do is, I'll sort of roam around and get my juice. I'm gonna turn off my audio until, because my voice is getting tired, till about 2:10 or 2:15. But you can certainly, I'll be checking on the chat, and we'll resume at probably 10 after, 11 after. I'll put the audio back on, and then we'll get going in full at 2:15, and we'll take this to 3:15, okay? And do the best we can. I'm going to turn my audio off, but I'll still be available through chat if you have questions. Oh, well, what's Tala's question? Okay, so before I take my audio off with the labs, so the labs are going to be interesting. We're not. I'm going to put video instructions. So for the most part with labs, this doesn't make sense to do it this way, I think is what you're getting at. And so what we're going to do, I'd hope the instructions were clear, but if they're not, I'll explain it anyway. It's no problem. What we're going to do is for the next lab, because I think you've already done the first lab, so that lab is just normal. The second lab I have data for, so I'm going to give you the data, and you're going to analyze it, and sort of pretend you already took it and follow the second lab. After that lab, I think what I'm going to do is I'm going to restructure lab, and instead of having the smaller labs, it's going to look a bit more like the long form lab report. So we're only going to have 3 or 4 reports, but I'm going to give you directions on how to use several simulations, and those will be made available on Blackboard. So you'll be able to watch those as many times as you need, work on them, and then during office hours, which I'm holding via Skype, you can just look at my, I'll just type in my, my Skype, my work address is my Skype address. So my Skype email is jd@lagcc.cuny.edu. So you can do that during office hours, and I can answer questions about the lab. I'm going to pretty much leave my Skype on when I'm available. I'd say I'll be there during my office hours, but I'd say just any time you have a question about it, it doesn't hurt to call. And if I'm getting called at times I don't want to be bothered, I'll turn off the program. It's not a big deal. So that's how labs will basically work. It's going to be, everything is unfortunately going to be a little clunky, but we'll do the best we can. And I think you'll get what you need. I do wish you could use equipment though. So yes, David. It'll all be on Blackboard, just like before. So okay, I'm gonna turn off my audio because I need to stop talking for. If I weren't sick, I'd still keep, but I'll answer questions over the typing for the next 10 minutes or so. Okay? All right. Okie dokie. Oh, yep, the lab instructions part is correct. So remember that we access this through the A section, the lecture section, is where you'll find the collaborate lecture that we're doing. And then the lab instructions will be in the B section, which I activated a long time ago. That's where it's always been. So good. Okay. All right. Let's see. Your experience is excellent. Moderator away. Okay. All right. I'm just trying to think about. Okay. So let's go full ahead. Everything is still visible? Yeah? All right. So we just finished talking about adding vectors using the parallelogram method. Again, you know, it's a geometric. You'll notice that we have algebraic expressions, but with vectors we have geometric interpretations of those expressions. So we can express this commutativity through this parallelogram method of addition. And again, you get one vector, click it in to the next vector. That gives you your A and B. The resulting vector is A plus B. But we can create this parallelogram where you'll notice we have start now here with B instead of A. And we click it into the end of A. And we can start at one vertex, our initial vertex, and go to where they meet. And we see that A plus B is indeed B plus A. Worth pointing out here as well that it's worth pointing out here as well that, oh God, okay. There's two of me in the video. You know, I'm not gonna figure that out. I'll just move the webcam to be a little more centered. There we go. You can see one of me, and then the corner of my room with the Dalek. So what you can see though is that going back to that question that was very good about the direction and the magnitude having to be the same. You'll notice here that in both cases, both the magnitude, the length, and the direction are exactly the same, okay? And that lets us know that that A plus B and B plus A are indeed the same vector. So it seems trivial, but again, you got to remember it's trivial when it expects it when things work like you expect them to. But then as soon as they don't, then it becomes an issue, right? And we're going to see with vectors that you will be your expectations will not be met sometimes with them. So we'll keep going. So vector addition is associative, which means that if you're adding a bunch of vectors, it doesn't matter which ones you add first with the parentheses. And you have here, what I like here is a nice little diagram of A plus B plus C. So you have A plus B plus C, right? And that gives you this A plus B plus C. You'll notice in any order in which you do it, you're always getting the same vector, okay? And this goes back to that question. If you want to reverse a vector, if you put a negative sign, you'll notice that this is B. Negative B, you can think of it as picking up the vector, right? The pen, turning it around. That's it. And you'll notice on the screen here, that's all we did. We picked B up, turned it around. You'll notice they're parallel, or they're actually, this is what the mathematicians like to call anti-parallel, bless their hearts, because they're going two different directions. And we can use this to define vector subtraction, okay? So you'll notice here we have, the vector, that's a good question. So So it's been important. It was pointed out to me a while ago that vectors are helpful throughout the entire course. So the Vectors Marathon is actually an extra credit assignment that has no due date. You can work on it all the way to the end of the semester. And if you find yourself struggling with stuff like momentum vectors, force vectors, angular momentum vectors, sometimes it's helpful to get insight into doing more vectors problems. One of my students once told me that she was able to, she found the course extremely confusing and challenging until she just did every problem at the end of the vectors chapter. And then when she did that, she found that the course was much easier. Everything made a ton more sense. So, and she did very well in engineering. So I took that advice to heart and decided to give you the opportunity to get extra credit to actually do that. So if that's helpful. So that's what the Vectors Marathon is about. Yeah, we didn't get to talk about that. Sorry, I forgot. That being said, no one has completed the Vectors Marathon yet. So if you can complete the Vectors Marathon, you would be the first. But that being said, could be a fun challenge. So back to vector subtraction. So you'll notice we have our 3 vectors here, and I sort of like this slide a bit better because these vectors are sort of just, they give you A, B, and minus B. And so now we want to look at the vector A minus B. So we take A, right? We have A here, and we can drag it to our triangle right there. And then we pick minus B and we add it in the same way, right? We take minus B, we stick the head or the tail here into the head. They connect like Legos. And then we have A minus B, and then we get the vector A minus B. So geometrically, it's identical, but we have to differentiate between the negative and the positive quantities. Okay, so moving on. All right. So I think this, oh, I see. So these rules hold for all vectors, whether they represent displacement or velocity. However, only vectors of the same kind can be added. So you can't add underneath here, this is rather annoying, this is distance and velocity. It doesn't work. You need to have distance plus distance. And I want to point out something to you really quick before we do the checkpoint. I want you to notice, let's look at our kinematic equations just briefly again. So we have delta x equals v naught t plus 1/2 a t squared. So we're looking at a constant acceleration situation here. Now you'll notice the unit of x, delta x, is meters. You'll notice here that the units are meters per second times second. This, that cancels, is in meters. You'll notice here we have meters over seconds squared times seconds squared, right? T squared. So when that cancels, the units here for this term are meters. So you have meters plus meters equals meters. Okay? I just want to point out that even though we're just learning about this, this seems like a seemingly new rule. It's not. All right? We've been imposing this all along. And in fact, it's a really good way to analyze equations, is when you have an additive term that you can only add like terms to like terms. Yes, Tala. No, we're just adding the units, right? So we're just saying that those are the units. So when I look here, let me get back here. So this is in meters, right? This is in meters, this is in meters, everything's in meters. We're not really adding m plus m. These are the things we're adding. Well, constants do matter, but the units are are sort of this extra dimension of quantity, right? They don't add to the addition or subtraction. They can multiply, right? Because in this term, the units multiply, but then your whole term has only one type of unit that can only be added to the same type of unit. So it's sort of an extra layer of complexity. It's more the way to think about it. Yeah. So again, the point here really is that, and it's a good one because it highlights this, is that you can't do the addition until you check to make sure the units all check out. So everything has to be the same. So this is meters. We multiply units here to make sure that it reduces to meters. Once we've done that here, we can check this is a consistent equation. Now that we know that it's in meters, we can start actually doing the math that's implied in here with the quantities. Okay, I hope that makes sense. But this is this is a good question. I really wish I was more there to answer it. But yeah, I hope that makes a little bit of sense. If it doesn't, we can talk about it more or ask more questions. Just type and I'll make it make sense. Don't forget, I will have office hours. Office hours will take place during normal office hour times. But like I said, I'll just be doing things around my house, and if I get Skype calls, I'll answer them. If I don't answer a Skype call, it might mean I'm on a Skype call with someone else who's having a one-on-one conversation. So just be patient. I'll get back to you. And if you're away, just we can play phone tag, or you can, if that doesn't work for you, we can set up an appointment a time. So I'm not going anywhere. So there's that. All right. So let's look at this checkpoint. Let's see if we can have some fun here. Let's see if this works for us. So it says the magnitudes of displacement vectors A and B are 3 and 4 meters respectively. Okay. And C is equal to A plus B. Considering various orientations of A and B, what are A, the maximum possible, and C, the minimum possible magnitudes for the sum A plus B? So what they want you to do is they're saying, okay, you have 1 is equal, oh, geez, anger. You have one here that's 3, 1 here that's, say, 4. That's not really good. That would be more like it. Okay, so say you have 2 vectors, give them arrows so they can have a life of their own. And you can pick these up and twist them around anyway, all right, so that they could be rotated or anything like that. So what's the biggest vector A plus B could be equal to, and what's the smallest that they could be equal to? Remember, if you can pick up the vector, you can certainly turn it around. Okay, so 7 for what? Max or min? Largest is 7. That largest part is important. You can't, context is not always clear. So we're going to say A, 7 is what I'm hearing. And 7 is gotten by getting one vector and adding it to another, right? The minimum, so it says what's the minimum magnitude? So the magnitude of -7, you'll notice, is still 7. So that is incorrect. -1, -1 or 1 isn't right because the magnitude would be -1 would still be 1. But you'll notice you can take 4, the 4 vector, and subtract off the 3 vector, right? I'm just doing this so that doesn't look crappy. So if you subtract that off, then you get 4 minus 3 is equal to 1. And you'll notice that anything else will have a little bit of both, and we haven't really done that yet. So let's see if our analysis is correct. I'm pretty sure it is. Yep. But what's more importantly than these answers is, does everyone see how we got them? Is that part clear? Because otherwise, if it's, yeah, I was going to say, otherwise I'll pick up pens, and that's a good way to see it. Magnitude can't be negative. The magnitude, yes. So magnitude of a vector, and we'll see this in a minute, magnitude of A, oh, that's not A, F, of, let's say a vector A is equal to the absolute value of that vector. I just saw a really funny video about math and physics classes, and we'll do things like pretend this is differentiable and things like that, and the math students get crazy because it's not differentiable at that zero. But it's physics. We're just gonna soldier through. Anyway, but yes, the magnitude is always positive. The magnitude can't be negative. Funny thing though, it also can't be imaginary. One of the powers of the absolute value function is to map to the real number line from the complex plane. It's actually one of its more powerful features. So it does not only ensure positivity, but it ensures reality as well, which is pretty cool. Okay, good. Hopefully we see that. And we can move on to components. Now, components can be a little tricky. All right, I usually like to in a room. Let's see. I think you can see. Yeah, you can see the corner of my wall, right? So the corner of my wall, you can have a little bit on this wall or a little bit on the other wall, right? And then you have a position that's a little bit of one, a little bit of the other. And so what we're going to see in looking at coordinate systems, and yes, this is our most mathy chapter, in case you're wondering. You'll notice that one thing to take notice of first is notice that we now are dealing with a coordinate system, but it is no longer x or y versus t. It is now x here and y here, meters, meters. So we have to be cognizant and careful about what coordinate systems we're looking at now. But you'll notice that the vector b they have here has the same kind of points. This vector b exists in this xy plane, much like as I said, my position in my room, a little bit of this wall, a little bit of that wall. You can see here there's a little bit of x. They say bx here is equal to 7, and by is equal to -5. You'll notice you're going to the minus here, and you're pointing into what would be the fourth quadrant, so that makes sense. And you have this b equals this little bit of y. So you can break this vector into two what we call components. All right, it has a little bit of x, the x component, and a little bit of y. Now, you can either do components, which gives you, so for this bx or by, or, and we'll see it here in a minute, you can do magnitude and angle. All right, these are two equivalent representations. Some of them are easier to use than others for other things. This is a little more intuitive for finding where a vector should be and geometrically interpreting. So when you're reading a graph, this might be more helpful to give you intuition of which way things are going. This one, right, you'll notice you just have these two components. You can't see right away what the whole vector is doing, but when you look at the components, I'm realizing that you can't see anything. This one being the components method, the x and y components, this will be easier for calculating. All right, so usually if you have a complex calculation you want to do, you'll want to use your components here. If you want to get an idea of where how a lot of vectors might resultantly, what direction they might go into, this one might be helpful. Again, two representations of the same thing. And one of the things we'll be learning in this chapter is how to translate from one representation to the other and how to define them. All right? So you can see that this picture has all of it. You have here b, which you can get the magnitude of b, and you have your angle theta here. You'll notice that typically the angle theta is given positively, but it is just as accurate to do a negative theta down here. But you really have to start being careful with your angles, because this is where you get into those, you know, you're sort of, this is really your first, it shouldn't be your first exploration into modular arithmetic, but what I mean by that is different values can be the same. So for instance, this can be 320 degrees, or it can be negative 40 degrees, right? Those numbers don't sound the same, but trigonometrically you get the same stuff. You're in the same spot. So you want to be careful there. So looking at that, do we have any questions on this stuff so far? The components can be positive or negative, as you see from the picture. And again, they are changed if the vector is shifted in any direction, but not rotated. That's going to be an important point later. Okay? So let's see. I didn't see a hand go up, so it's okay. We can go back to, I'm realizing, trying to get it to go the best here. So if something's delayed. So you'll notice, of course, I forgot I made a bigger picture here. Again, this is just showing that this is a more clear picture. So if you want to write that down or really take a look at it, you can see it there. Okay, I'm actually making okay progress. So now we want to talk about, remember I talked about that, oh, yes, Zilla. Oh, okay. Yes. My microphone doesn't work, Zilla, so you'll have to type out the question, unfortunately. Or my microphone works, but I'm still not hearing the students for whatever reason. So, and I don't know why I'm talking to the chat board. I should talk to you right here. Ooh, good question. The XY axis indicate the components, but they aren't the components, right? So let's go back to that picture, which is a better place to look at, make this point. So the X and Y axis are just the X and Y axis, but they help us label and identify the components. And I want to show you what I mean by that. If I were writing this in component form, I would write this as, let me get to the pencil, I would write that B is equal to 7. And again, this I hat is the component part. So you could say this is the x-axis part, minus 5i. I'm going to explain what these unit vectors are in a minute. We're not quite there yet. But this is what this would look like mathematically, this vector B. Okay? So the components are described by the x and y axis, but I wouldn't say they are the x and y axis. Yeah. Yeah, I don't use that notation typically, but yeah. All right, Tala, what's your question? Well, we're gonna talk about that in a minute. I don't want to say David just wrote I equals x and j equals y, so we're gonna talk about unit vectors in just a second. I'm not quite ready to go there. I just want you to. I wanted to address Zilla's question about what the nature of the x and y axes here. Yeah, no, definitely. This part right now will be confusing because we have not defined this yet. These have very special definitions that link them to the x and the y axes. Okay, so we'll do that. Okay. Tala had a question though. Oh, I see it now. Is B the average of the two? No. B is the magnitude of the two, and we're gonna look at that in just a minute. So we're actually talking about this topic right now. So let's see what B is. B would be the magnitude of these vectors, and I think you'll notice if you have you'll notice that you have two legs of what's going to form a right triangle, and that will start to give you. You can notice you could transpose B here if you want, and that this is the hypotenuse of a right triangle. So I think you'll be able to guess what B is, but we're going to see it explicitly in the very next slide. So let me clear this. So let's take a look at this slide. We're going to sort of go back and forth between these two. You'll notice that you have your components in 2 dimensions. So let's make a triangle. Well, first we're going to need. I want my hand here, and I want my hand here, so I'm going to move this. Okay, this is just going to be annoying. All right. So let's take a look at our components and our magnitude and vector and angle representations. Okay, so this is all done by looking at a triangle. So take a look at this slide. I want to try the sharing a blank whiteboard here for a second. Let's see how this works. Okay, so I'm going to make some lines. I want to make a triangle and describe this whole process. So keep in mind that last slide we saw. If you want to screen capture it or something, we're going to see it all and go back in a minute. But we want to make a triangle. So we have one line. We have, oh no, it's not going to be perfect, but well, you know what is in this pandemic world we live in, right? Oh, crap. That was just a little too unacceptable. So one, oh no. Let's do a line. So I'm not going to make a big deal out of this. All right, that's going to be our triangle. It's not great, but what are you going to do? So when you're looking here, this will be our vector. Oh, I don't like that. It won't just let me erase part of it either. So we want to make a vector A. All right, I'm just going to make a vector here. So this will be our vector A, and you'll notice that I'm not going to label it yet, so might be a little confusing, but you'll notice we have a horizontal or an X component and a vertical or Y component. I didn't finish it there, but that's okay. I'll try and fill it in here because I'm anal retentive. All right. Now we have this part here, which will be theta. So if we call this AX and this AY, right? This is just sort of traditional X and Y axis. We're putting our origin here. I'll just make I just can't make anything very straight, so call that X, call that Y, right? So if you'll notice with this triangle, if we have AX, my X's and Y's are looking very similar. If we call this AX and this AY, and this is A, you'll notice that the magnitude of A, the length of A, right? A squared will be equal to AX squared plus AY squared, right? Let me go, hold on. I want to be sure I'm back in the chat here first. Okay, so hopefully we can see that, and I hope that makes sense. So we can see that from the triangle. Now, from there, we can, that's the easiest one to see. Now, looking at the other ones are pretty easy. We can use our whatchamacallit, our SOHCAHTOA, if you remember that. I don't know why the camera's not facing me. Hold on. Now all you guys can see my lunch now. Yeah, I guess that's a way to look at it. It's the resultant vector from the components. Let me make this camera get back to. It's not cooperating. Hold on. I'm going to move it manually. All right. I don't know why it moved. I don't know why any of the computer stuff does what it does. Okay, so if we use our SOHCAHTOA, right, for this angle theta, we know that we'll have some relations here, and we know that the for instance, we do know that the sine of theta, right, will equal the opposite. So if this is theta, the opposite over the hypotenuse, right? So if we want to do that, we can write this as AY over A. And then we can write, we can go down and we can write cosine theta will equal the adjacent, which if you look there is A of X over the magnitude of A. And if we look at the tangent of theta, I'll point all these out in a minute, don't worry. AY over AX. Okay, so let's take a look at that in the triangle, the pad of doom. Okay, so you'll notice that this crappy looking, that's A sub y, it's supposed to be opposite over hypotenuse, right? Cosine theta is equal to adjacent over hypotenuse, and the tangent theta is opposite over adjacent, right? So that's where we get, all we've done is use Math 200 to get these. Yes, this is the Pythagorean theorem here, absolutely. So you'll see here that using the Pythagorean theorem and our definitions of sine and cosine from the triangle, because we have a right triangle, we now have equations that relate our angle and magnitude to our components. And what I want to show you is, if you have all this written down, is these two equation. Oh, Jesus, I was about to write in red pen on my stupid tablet. That might have been entertaining for all of you, but I would not have been happy. So these two equations will connect our, you'll notice you have magnitude and angle on one side and components on the other. All right? So that means that these ones, you'll notice that you can do the same thing. You can multiply both of these by the magnitude of A on both sides, and if you see that, I'll let it stand. I'll let you copy it for about 10 seconds, but remember, we're recorded. The thing is it'll clear once I move on, but once we get back into, well, maybe it won't, but once we get back into the files, once we get back to the lecture, it'll all make, you'll see where we're going with this. So if you have that, if come back and look at it later if it doesn't make sense. But let's go back to the lecture. Okay, it's just going to be a pain in the butt. And you can see here that when you solve, when you solve for AX and AY from that previous slide, you get your components. And you'll notice again, you have, if you look at what's going on here where I'm pointing, you have your components on one side and your magnitude and angle on the other side. Same thing here. You'll notice it's that Pythagorean theorem from that triangle is written here. And you'll notice again, magnitude quantity on one side, components on the other. Magnitude quantities and angle quantity on one side, components on the other. So what this lets you do is transform seamlessly between the magnitude angle representation and the component representation. This skill is crucially important for the rest of the class. You'll be doing this constantly. Remember how I said the course is cumulative? I won't ask you a vector question, but every question you have will require you to have this knowledge of vectors, right? What I mean by that is I won't ask a chapter 3 question on the final, but in order to do a chapter 13 question, you have to know how to do this. This skill does not go away. And that's why the Vectors Marathon exists. Oh, I got a chat bubble. Oh, no, I'm just going crazy. We say magnitude, but length of the vector is an appropriate way to say it. The reason why we say magnitude is because length, you don't want to start, when you talk about velocity vectors of the length of velocity vector, you're not technically incorrect, but you could very easily get confused. And we're sort of still in that confusion state. So, it's better to say magnitude. Oh yeah, no, I know. The math people do their, bless their hearts. Bless Calc 3's heart. You'll get really mad when we start taking the derivative of absolute values. That's when things get crazy. So okay, all right. So let's take a look and see if we can manage this one. We have a 3-dimensional case. We need more components to specify a vector. So they have that here. We're going to worry about this a little bit. Mostly we're going to worry about this z component. So if you have, if we, let me see if I can go up to the corner. I don't want you to all see what my house is falling apart, but the things we do for education. Let me see if I can, hold on, I'll just tip the camera. If you can see the corner, right? The corner, that would add an XYZ axis. Corners are very natural for this. So that's what we'll do there. But that being said, this whole thing is, yeah, all right. This whole thing is weird. We won't do much with the A phi, theta phi. Spherical coordinates are hard. That's what we should know about them. So that's kind of the way it is. So let's look at this checkpoint. Hopefully you figured it out. It says in the figure, which of the indicated methods for combining the x and y components of a vector are proper to determine that vector. That means in which way are these consistent? Okay. So looking at these, I think what that's going to mean is which one of these really represents the x and y components. So let's go through and take a look at each one of them. All right. So for A, is this one going to be a little bit of, there's 3 things to look at here. Is this one going to be a little bit of x and a little bit of y? It kind of looks like it, but I would think that this vector would start at the origin if it was really going to be described this way. And I think we can eliminate just about every one that doesn't start at the origin. You'll notice this vector starts here. This vector starts here. So I think we can cross A and B out. I think in order to break things into components in this x and y way, we're going to need to start at the origin. So even though this one looks weird, this one is correct-ish. D works very nicely. D is, I think, clear according to Hoyle projection. The ones I'm getting rid of here immediately are the ones that where the vector doesn't start at the origin. Because usually when we're analyzing, when you're dissecting a vector, it always starts at the origin. So when you look here, D, and I would say if you look here at F, definitely. I don't know if this is improper, because I do it this way. So this isn't incorrect, because you'll notice we start very nicely at the origin. You can do X here, and you can certainly transpose Y. There's nothing wrong with that. I would not mark this incorrect on a test, but they might have an issue with it. So let's see what they say. Oh, right, I'm not. No. Oh, hold on, Tala. So they like C, D, and F, and that's what we had, right? If you recall, we had C, D, and F. And notice why we cross these out. It's right at the origin. So what is your question, Tala? Did you type it out? Oh, why is it incorrect? Which one? Yeah. So again, it's about this word proper, right? So when we're doing vector analysis, let me delete because I made a mistake there. If you look at the ones that are correct, which are C, D, and F, right? Those are correct ones. If you look at these, each vector starts at the origin, and we need that. And when we're looking at something in terms of x and y components, we do have to agree on the origin. So that's going to be, sadly, that's going to be important. Because if we have different, because what we'll want to be able to do is shift axes about an origin, and so we will have to agree on where the origin is eventually, and that's going to keep our analysis very simple. So here, if you're looking at your Calc 3 stuff, you might be saying, well, this is kind of true, but for our analysis, in order to do an analysis and have these components match up in a meaningful way, the vector does have to start at the origin, which is why we can cross this one out, and this one out. And I'll circle where each of these vectors starts. The vector A starts there, and that one. Vector A starts here, and vector A starts here. You'll notice none of those circled points are the origin. Okay, does that make sense? Only when analyzing it. Yeah. Okay. Good. Checkpoint cleared. All right. Let's see here. Moving on. All right. So vectors and their components. So this is just a nice. We already went over this slide. And keep in mind. Be careful going between radians and degrees. It's a peril pitfall that befalls everyone. So now we're finally going to, and I did want to, good, I got 20 minutes left. And by the way, for attendance, I'm just going to be, I'm going to probably go back and look at the recording of this to mark who's here. And all you have to do to be here for the week is just do something. I mean, it's a really imperfect system. So if you turn in work, if you do something, you're here. For the VOE roster, everyone showed up beforehand. The only place this is a problem is in astronomy. You're not astronomy, so we can let it go. So just say something in chat, I guess. Oh, no. I have a whole thing here that I can screen capture. I have the list of participants. So I'll probably just take a picture of it. You know what I could do is I could take a picture of it with my phone, and then I'll fill it out later. It's no big deal. So I'll do that. But yeah, or if you say something in the chat, I can go back and look at it. But this should be up too when I look at the participants, unless it's just the log in the chat. But like I said, I'll run and get my phone and do that later. So I will. Let's go through and make some sense out of that mystery of the unit vector and the unit vector notation. All right. So now, they're introduced, right? The I-hats and J-hats have appeared. We've used this before, and it confused everybody. So these are called unit vectors. I'm underlining them. All right, and you'll notice here, this is where we talk about them. They're on an XYZ axis system. I realize you can't see that. They're on an XYZ axis system. And you'll notice that in the X, we assign that the I-hat direction. The Y direction is assigned the J-hat direction. And K is the K-hat direction. Now what you should be asking is, what the hell is I-hat, J-hat, and K-hat? Well, I'm about to tell you. And it's listed here. So unit vectors are vectors, but they're very special and behave a certain way. They always have a magnitude of 1. So if you were to take the magnitude of A, let's do that really quick. If you were to take the magnitude of A here, what is going on? Like that, we would say, you could look at that and say, okay, I need to take the magnitude of A, I-hat, plus AY, J-hat. right? So when you're taking that magnitude, you'll eventually come up with terms where you're taking the magnitude of this just I hat part, and that will equal 1. And the magnitude of j hat will also equal 1. All right, you'll notice that if you make this, if you break it into components, like in the x, oh, darn it. If you break it into components here, like x and y, and let's do that. I'm going to make a triangle. I'll make a simple triangle here. Da, 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 da. Oh, what am I doing? I'm going crazy. I just want this here, and we'll change the color to red, and we'll make a nice little unit vector here and a unit vector here. All right, so they're the same length, and basically, if we take their magnitude, right, it's 1, and you know, this has a magnitude of 1 and this has a magnitude of 1, which means that if you were to take the hypotenuse here, it would have a, you know, you'd have a, whatchamacallit, the length here would be √2, right? And that's the whole idea, is that this is always equal to 1. If you take the magnitude of this component, it's 1, 1, everything is 1. That's where the unit in unit vector comes from. It has a particular direction. I hat will always be associated with x, j hat will always be associated with y, k hat will always be associated with z, with of course the caveat that that is the convention of physics. Math may have different conventions, so you're going to have to always know your context. Knowing context is incredibly key. Always got to know your context. In the context of physics, you can be comfortable in this setup here. Okay? Now, it lacks both dimension and unit. Well, why is it called the unit vector? Because here we're using the mathematical definition of unit, which is 1, right? That if that makes sense to you, yeah. But I have a feeling that what might not just jump out at people. But yes, that is true. The only reason, Elvin, that might be where I might, because the answer is yes, but there's a but there. Remember when you do a 1, 0 like that in your, so what Elvin wrote, just to make it bigger, is, oh, wrong side. Because, you know, when you write it like this, 1, 0, in math, yes, you're fine. But in physics, this 1 might have a velocity, an acceleration. It's not really summed up well. So that's why we don't use the math notation very much here. You know, you want to be careful, because here with unit, we're very much talking mathematically with this unit of 1 here. Whereas, and then in a math class, sure, that works. But in physics, we need a little more context with our data we're presenting. It doesn't just automatically translate. So, as always, be careful. So, we want to notice that it's also labeled with a hat. Okay, we use the right-handed coordinate system in physics. That means that up is positive, down is negative. To the right is positive, to the left is negative. That's how we do it. Again, it's just our convention. Does this make a little more sense, the notation? And I want to do a quick example. Let's go back to what we wrote earlier, which was, oh, gotta select the pencil, which is that remember that b vector when I wrote b equals 7i minus 5j? That's how I'll write unit vectors in this class. You'll notice that if you look at b here, bx, right, was 7. by, oh, I forgot, you can't see that part. Bx was 7, and by was minus 5. Okay? And then all you have to do is express it this way, and it tells you that 7 is exclusively in the I hat direction, all right, or the x direction. Minus 5 is exclusively in the y direction. They go down. And then this gives you, separating them this way gives you, with the I-hats and the J-hats, gives you a clear identity that will actually translate pretty well into mathematics to manipulate these vectors and add them, multiply them abstractly and get correct answers without having to do geometric visualization all the time. Okay? So that's the unit vector. I think we have an example coming up next, but does that example make sense? Are there any questions on it? This is pretty important, so I'll give you a minute to sort of think or type something out for a second. I got people leaving and coming. I'm guessing connections can be a little rough. Okay. All right. Again, you'll have this will be recorded and you'll have access to it later if you want to watch it again. And of course, you'll be able to fast forward through it, which will probably be amazing. Or play it at 1.5. Although I think I talked too fast. I don't think anyone would want to really hear it at 1.5. But anyhow, so again, looking here, I don't know why this is all messed up. This was not messed up when I did this before. Our J-hat, or our components, these are X and Y components. You'll notice they exist in both vectors. And then I-hat and J-hat indicate the unit vector components. All right? Now the quantities AX and AY by themselves are scalar components. All right? Or just components. We'll call them scalar components. And vectors can be added using components. This is probably the most powerful thing about components that I love. So remember all that geometry? That's a lot of work. If you have R is equal to A plus B, the X component of R, you'll notice is the AX plus BX component only. Same thing with Y. You'll notice you get AY plus BY. And for Z, AZ plus BZ. So all you have to do is add the components. Wait a minute. All you have to do is add the components together. All right, you'll notice you have X and X, Y and Y, Z and Z, and you can get the whole vector. Now this seems great, or might seem trivial, right, with A plus B here at the bottom. But if you have R equals A plus B plus C plus D plus dot dot dot, you can already see where this is going, right? This could be truly awful. And although it's tedious, and it is tedious, it works and it's simple, right? Simple and tedious, you have to make these decisions, right? Simple and tedious versus elegant, and if you spend 4 hours trying to figure out the one line when you could do it in 10 lines but not have to worry so much in a half an hour, what's really worth doing. So keep that in mind. It makes components make things much easier to handle mathematically. Okay, so I think I'm going to skip this checkpoint because I can't go quite. I'm just noticing I can't quite go at the pace I want to, and I think we've beaten components to a dead horse. But let me go back so you can do the checkpoint yourself if you want. You have the answer there. You can check it out and work on your own. If you have questions about why an answer is a certain way, you can ask during office hours or in the next lecture. So I want to continue on, but I want to talk about that homework problem first because we only have a few minutes left. Let me see here. Where are we gonna go? I think this would be a great place to start next week. So not next week. I'm sorry. Tomorrow. Don't get too excited. We'll be meeting tomorrow, just like we did today. So let's do that. Let's talk about the homework. Okay. And actually, let me get my my phone first. I'll be back. Hold All right, I'm back. Let me, oh, I have to allow this again. It's, you know, I'm doing the best I can. So let's go over that problem from homework 1, okay? Because some people have asked about it, and it's a good way to spend the last 5 minutes. Let's go to the whiteboard. So a lot of people are struggling with the first problem on the homework, which was about the centuries and the different days, right? So basically, the long and short of it is if you look, right, this could be the last day and the first day. And I don't know if someone wants to give me specific numbers, that would be helpful, but I'll just make some stuff up. About homework 2, chapter, I was hoping Wiley Plus would make the same announcement. Oh, has anyone heard about Cengage making the semester free? Yeah, I would say Wiley Plus, unfortunately, has not decided to go the free route, which is disappointing. They may eventually, but I don't know what to say. They're awful. But that's what we've been using for a while, so that's what everything's set up on. So it's unfortunate, but it is what it is. If you want to use Cengage resources or a free resource, someone sends you something and you want to use it for free, then you think it'll help you, go for it. Anyhow, looking at this problem, so basically the idea is that at the end of, say, 1,000 years, the day is something like 24 milliseconds longer. I don't know. It's something like that, right? But each day is 24 milliseconds longer. So that means that the day right before is nearly 24 milliseconds longer, right? And the day right at the start here, which is exactly the same as it is today, has a very small, minute change. And it's too difficult, here would have the small, minute change. And it's too difficult to add each and every single day, right? So the trick here is you sometimes reality is not helpful for you, the way things actually work. You have to come up with a representation that is helpful. And the representation that is helpful is, well, what if we could make everything the same? So think about an auxiliary problem, right? What if you had to add the numbers from n between 1, 0, and 100? Well, you could go 1 plus 2 plus 3 plus 4, and that would be annoying, right? Or you could recognize that you have 0 plus 100 is 100, right? 99 plus 1 is 100, equals 100, right? You make bins in which everything is the same. So you want to turn this line, right, into a flat line in which all the time variants are the same. And you can do this by taking an average value and then doing some unit conversions. Now, this does not represent reality because this isn't how the changes actually happened, but it's an equivalent picture, that's easy to deal with, because then all you have to do is figure out the number of days, and when you take the average, you'll get the time change by 1 day, average it over the total number of days, and that will give you your average. That will let you know the total amount of time you've lost or whatnot, or whatever they want you to find. But that's the trick to this problem, okay? So I hope that worked for everybody. I'll try and work on. I realize everyone's got a favorite program, and there's seamlessness and unseamlessness to all of them. For instance, with this program, the recording and getting everyone sort of organized by class is just very easy, but this microphone issue is upsetting. How is A equal to AX? Oh, that's a definition, Alvin. That's just a definition of how we represent vectors. So let me go back to the PowerPoint there. I'll just say, that I'll stay on a little bit to talk about that. Yeah, no, I think so too. Yeah. There should, look on some YouTube videos for the Wiley Plus answers to submit. There's some YouTube videos on how to write stuff. It should be okay. That should help you do it. Otherwise, there's intro stuff. I mean, don't worry. We have some flexibility there. Because I like I said. Oh, right, I didn't tell you guys this. I told the evening class. So homework's going to be due a little differently. I'm going to do the homework is going to be due before the first exam. So please don't worry about the due dates for homework 1, 2, or 3. It's all going to be due, and we're going to push the exam back. Because we just lost a week. I don't think I really have a choice. I'm not thrilled about doing it in spring break, but I will tell you, you can read about the exam, how that will go, but we'll talk more about that at a future time, okay? And to answer the question, I want to go back to the slideshow. Again, I'm not going to use the math vector notation. It is the Elvin's notation is correct there in the chat, but let me go back to sharing the content here. Files, chapter 3. Chapter 3. Oh, chapter 3. Share now. Okay, and will it let me scroll? It will not let me. Oh, it's decided to let me scroll. That's very fancy of it. If we go to our definition of unit vectors, right? So if we go here, why is it this way? This is how you write vectors in unit vector notation. So if we take a vector A, let me get the pen working here again. If we get a vector A, okay, like so, we can break this into Cartesian components. I'm doing this pretty poorly, but we're just using a Cartesian coordinate system to represent a vector, okay? So we have some vector A. When we use the Cartesian coordinate system, it is the Pythagorean theorem, yeah. Well, that's part of it. But when we do that, we'd say, okay, let me do this let me delete this part here because I want to do this correctly. So let's do it one step at a time. So we have this vector A, right? And that's just some vector. So now the question is, what the whole place where this comes from, this representation is saying, oh, I want to describe my vectors with a certain coordinate system. So when I do that, I'm going to change my color here to blue, back to blue, and I'm going to make lines. I say, okay, now for this vector A, it's just some vector, I'm going to put a coordinate system onto it. This is a little better, but it's not perfect, but I hope you're all okay with that. And now I can say, so now I have my AY coordinate, right? AY will be some here like this, or that will be actually more like this, So it'll be AY. And I can go, and this is my AX coordinate. So AY and AX come from saying I need a saying I need a coordinate system for the vector. And once you do that, then your I hat and J hat are features of that coordinate system. Okay, so that's how you handle that answers I think this very important question: why do we have things built like this? Okay, and with that question, I'm still going to be on, but I'm going to stop recording because I want the video to have time to process. Okay, so let's see here. I'm going to go here, and we're going to